Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element mercury. Now, I have a little sample of it right here in this vial. If I tilt it to the side, you can see the mercury roll around from one end of the vial to the other. And I did actually put this on my scanner, but even if I magnify this, it doesn't look as nice as just looking at it in person. I'm sure you've seen mercury on your own as well, and I have some better photos that we'll use later on. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to go pick up. His fantastic website, periodictable.com, is also worth visiting. Mercury is the 80th element in the periodic table. Its atomic number is 80 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Mercury was one of 11 or so elements discovered prehistorically because it occurs in its native form on the surface of the Earth. It was discovered well before the invention of the written word, so I can't detail its discovery, but that won't stop us from discovering lots of fascinating things about this element. Mercury is also part of a large group in the middle of the periodic table called the transition metals. This section of the periodic table is where we fill the d electron orbital of the respective atoms as we move from left to right across the periodic table. The element Mercury is named for the planet Mercury, the fastest moving planet in our solar system. Of course, the planet was named for the wing-footed Roman messenger god. The graphic symbol for the planet is also the alchemical symbol for the element. You may have wondered why the chemical symbol for Mercury is Hg and not something like Mr or Mc. Turns out, Mercury was formerly called hydrargyrum, which was Latin but derived from the Greek hydor, meaning water, and argyros, meaning silver, liquid silver. Mercury is still often called quicksilver. Anyway, the Hg symbol is taken from this older name for Mercury. Mercury occurs in its native metallic form in nature. Here we see droplets of mercury in feldspar. And here we see native metallic mercury coating the surface of this beautiful sample of the mineral cinnabar. Cinnabar is the most common source of mercury in nature and has been mined for thousands of years. In addition to its mercury content, it's been used as a red pigment. More on this later. Cinnabar is mercury sulfide. In 2019, the world produced around 4,000 metric tons, or 4 million kilograms, of mercury annually. That's been reduced to less than one-third that amount as of 2022, but back in 2019, China was the major producer of mercury with over 87% of the world's production. All others pall in comparison, as you can see. In 2022, there were 1,160 metric tons, or 1,160,000 kilograms of mercury produced. That amount of mercury would be a cube, only 4.41 meters on a side. Let's throw in an average person for comparison. Still, a lot of mercury. Mercury production has varied widely over the years. Here we see production from 1900 to 2022. Production peaked in the early 1970s. As restrictions on the use of mercury have become more common, not as much is needed. Today, production is only 1/10 what it was in the 1970s. Currently, mercury is going for about $30 per kilogram. Surprising, since it's about as uncommon as silver, which is 30 times as expensive. Here's how the price of mercury has varied from 1900 to 2018 in inflation-adjusted 1998 dollars. Looks like a pretty hard-to-predict market. The element mercury is not really common, coming in as the 61st most abundant element in the universe by mass, only 1 part per billion. 20 times as abundant in the Sun, it makes up 2 parts per 100 million of its mass and is the 33rd most abundant element there. It's the 51st most abundant element in meteorites at 2.5 parts per 10 million. Very uncommon in the crust of the Earth, it's the 56th most common element at 6.7 parts per 100 million, about the same as silver, its neighbor to the left in this chart. Mercury is rarest in the oceans of the Earth, making up only 5 parts per 100 billion. But there's a lot of ocean, which means there's 20 million tons of mercury in the waters of the Earth. Lastly, and like many of the elements in the upper reaches of the periodic table, there's no free mercury in us, or at least there shouldn't be. Most people do have a little bit of mercury tied up with other elements, as we'll see. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own, showing that element's growth over the age of the universe by various processes. Mercury is here. I understand this looks complicated, but let's look at just Mercury a little closer. The horizontal axis of this square represents time, from the Big Bang to now. The vertical axis shows the proportion of mercury created by various processes relative to the Sun. About 2/3 of mercury present today is believed to be produced by dying low-mass stars, the magenta area. The rest is produced in supernovae, the yellow area. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 80 protons for mercury. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 40 known isotopes of mercury, and of these 40, there are 7 non-radioactive isotopes. There are only 6 elements with 7 or more stable isotopes. These isotopes occur in nature in varying amounts, as you see here, from 0.15% to almost 30%. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of mercury occupy the same place in the periodic table. Of the radioactive isotopes of mercury, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest mercury half-life is Mercury 194, with a half-life of only 444 years. That may seem like a long time, but compared to the 13.8 billion year age of the universe, it's not even a blink of an eye. That's why we don't see any of these isotopes out wandering around in nature. They've all decayed away by now. If you want to experiment with these, they must be manufactured in a reactor. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of dividing by 2. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms. And so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice that there's 1 remaining atom after 10 half-lives. If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Mercury has a fairly high density at 13.534 grams per cubic centimeter. As a reminder, water has a density of only 1 gram per cubic centimeter. I've put up more densities for you here. As you can see, mercury is somewhat denser than lead, and we all consider lead as being a pretty dense element. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, mercury's density is 13.534 grams per cubic centimeter, the magenta circle. It's denser than lead, but quite a bit less dense than tungsten. Except for the fact that it's a liquid at room temperature, a cube of this stuff sits neatly between my tungsten and lead block. Unfortunately, it's hard to make a room temperature block of a liquid, and the fact that if it got loose I'd have a toxic mess to clean up. Mercury spills are notoriously difficult to remediate, so I'll give up on owning a block of mercury. This video demonstrates the high density of mercury by floating a large anvil. The steel anvil is about 1/2 as dense as mercury and floats quite high in the mercury pool, with about half of the anvil above the surface of the mercury. Don't do this one at home unless you want to pollute your neighborhood. A human standing on a pool of mercury would only sink shin deep, but it would be almost impossible to balance and remain standing. Mercury is one of 2 elements which is liquid at room temperature, the other being bromine. Therefore, its melting temperature is less than room temperature, minus 38.83 degrees Celsius, or minus 37.9 degrees Fahrenheit, as a matter of fact. You can easily freeze mercury with dry ice, CO2, which is at a temperature of minus 78 degrees Celsius, or minus 109 degrees Fahrenheit. There are places on Earth where mercury would be a solid, like the South Pole, where you see me standing in minus 40-degree temperatures at the height of summer, though it was actually midnight when this photo was taken. No, I didn't bring a sample of mercury with me, but I wish I'd thought of doing that. Mercury boils at a very low 357 degrees Celsius, or 675 degrees Fahrenheit, giving it the 79th highest boiling point, or the 15th lowest boiling point, of all the elements. That's less than 400 degrees Celsius above its melting point, giving it the 80th largest liquid temperature range of all the elements, or looking at it the other way, it has the 19th smallest liquid range of the elements that we know about anyway. Not all of the elements are shown on this chart. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest, so here it is. The widest liquid temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range. That goes all the way down to neon, which is liquid only in a 2.51 degrees Celsius range. Again, mercury has the 19th lowest liquid range at 396 degrees Celsius. Notice all the noble gases and hydrogen have very small liquid temperature ranges. If we compare the size of the mercury atom to that of hydrogen, we'd see something like this. The mercury atom is about 3¼ times the size of hydrogen. Here's the electron structure. By the way, a picometer is a trillionth of a meter. Atoms are seriously small. Looking at all the element atom sizes, here we see them sorted from largest, cesium on the top left, to the smallest, helium on the bottom right. Mercury has the 38th largest sized atom of the elements, about in the middle of the pack. Mercury, however, is the king when we talk about thermal expansion. Mercury has the highest rate of thermal expansion of all the elements, a whopping 1.81 parts per 10,000 per Celsius degree. This means if I filled a 1-meter long tube with mercury and heated it by only 1 degree Celsius, it would get longer by almost 2/10 of a millimeter. You could actually see that. And that's only heating it by a measly 1 degree Celsius. That's why mercury found widespread use in thermometers, something we'll touch on in a bit. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. Mercury has a moderately simple set of emission lines across the spectrum. If I increase the contrast to remove the background, you can see those colors more plainly. In my experience, the red lines are not quite as prominent as you see them here, and there are extremely bright ultraviolet lines that I'm not showing here either. This is the visible spectrum. We'll get to those ultraviolet colors in a bit. These emission colors uniquely identify the element as mercury to scientists. No other element gives off this set of colors. Let's take a look at a few applications of the element mercury. Often, mercury is used in extracting native metallic gold from ore. When you mix crushed gold ore with some liquid mercury, it combines with the gold to form a soft amalgam. That ball in the miner's hand is a gold-mercury amalgam. You can then heat this amalgam to vaporize the mercury, leaving you with only the pure gold. Without strictly controlled equipment, this is extremely hazardous. This type of gold extraction is responsible for considerable mercury pollution in California today, even though the gold rush was over 150 years ago. On the lighter side, I had one of these toys as a kid. It contained a bead of mercury. You navigate through the maze by tilting it in different directions. You can see the bead of mercury here. Needless to say, this is no longer sold. Until very recently, mercury batteries were a thing. But due to concerns about recycling and the mercury content finding its way into the environment, these batteries have been banned in most countries. If you spin a very round dish of mercury, the surface forms a parabolic mirror, perfect for a telescope and much cheaper than casting, grinding, and polishing a glass mirror. Liquid mirrors are actually about 1/25 the cost of an equivalent-sized glass mirror. Of course, you can only look straight up with this type of telescope. This is the 4-meter diameter International Liquid Mirror Telescope located in India. It contains about 50 liters, or about 700 kilograms, of mercury. The telescope has been observing since March 21st, 2023, and is looking at precise star positions and variability in brightness of the stars that pass over it. This could show the evidence for exoplanets. Remember that spectrum of mercury I showed you a bit back? Let me add those extra ultraviolet colors given off by the excited mercury I didn't show you. Here they are. These intense ultraviolet colors are used in the common fluorescent lamp. But it takes more than just mercury. Here's a special fluorescent lamp. Half of the tube is only clear glass, and you can see the visible baby blue glow of mercury. You can't see the intense ultraviolet light given off. The other half of the tube has powders coating at the inside. These powders glow or fluoresce when hit with ultraviolet light. Look at how bright that half of the tube is, and imagine how much ultraviolet light the mercury in the tube is making. If I magnify the clear end of the tube, you can see the tiny mercury droplets condensed on the glass. Neon signs are another example of mercury vapor-filled tubes glowing with light from ultraviolet fluorescence. Neon signs are mostly a misnomer. Only the red tubes contain actual neon gas and no mercury. All the other colors are usually created with mercury and various fluorescing phosphor powders coating the insides of the tubes. So really, most of these should be called mercury signs. My thermostat at home contains a bimetallic coil of metal that unwinds when it gets hotter. A vial of mercury with electrical contacts at each end is attached to this coil. Watch as I heat it with a hairdryer. When it tilts far enough, the mercury rolls to the end of the tube, making contacts to turn on an air conditioner. I don't actually have an air conditioner. I live in San Francisco, and we use the cool Pacific Ocean for that. There are contacts at the other end of the mercury switch, so when it gets colder, it turns on the heat. Thermostat means constant temperature. Thermostats no longer contain mercury switches. My house was built in 1989 when they were still legal. This device is smack dab between the last slide of the thermostat and the next slide of a thermometer. Here, there are electrical contacts inside the thermometer. When things heat up, the mercury rises and makes contact between the two wires, switching some other device on. Which brings us to the thermometer. This particular thermometer was used for measuring body temperature orally. They're now illegal because of the toxicity of mercury, but this is typical of mercury thermometers. A large reservoir of mercury is held in a bulb at one end. When heated, the mercury expands and is squeezed up a very thin tube called a capillary tube. The higher the temperature, the higher the mercury is seen in the tube. Here you see the thin capillary tube magnified by the shape of the enclosing glass, indicating a temperature of almost 99 degrees Fahrenheit. Here's a much more typical lab thermometer. It also has a rather large bulb of mercury. This is the problem with mercury thermometers. They're made of glass, and if they break, you have a toxic spill on your hands. For this reason, many states in the U.S. have banned the sale of mercury thermometers, and the U.S. standards body, NIST, will no longer calibrate these. Indeed, 140 countries have agreed to reduce and regulate the use of mercury. There are plenty of safe alternatives to mercury thermometers. And here's one of those alternatives. Since we can't use mercury in thermometers anymore, material scientists came up with Gallinstan. It's an alloy of 68.5% gallium, 21.5% indium, and 10% tin. It remains a liquid well below the freezing point of water. It melts at a fairly low -19 degrees Celsius or -2 degrees Fahrenheit, so it's a liquid at a wide and useful range of temperatures. Also, Gallinstan is not as toxic as mercury. Curiously, Gallinstan expands almost as much as mercury with temperature, making it useful for non-toxic thermometers. The other possible substitute for mercury in thermometers is liquid alcohol. Here, the alcohol is dyed red to make it more visible. Before our age of digital, well, everything, Atmospheric pressure was often measured with a mercury barometer like the one you see here. It's really a simple device in principle. You fill a 1-meter closed-end tube completely full of mercury and invert it into a mercury reservoir. The mercury in the tube falls, creating a vacuum at the top until the air pressure pushing down on the surface of the reservoir balances the weight of the mercury in the tube. Measuring the height of the mercury column in the tube and knowing the diameter of the tube and the density of mercury gives you the pressure at the bottom and hence the atmospheric pressure as well. Nowadays, these barometers have almost disappeared, and atmospheric pressure is measured in other ways that's less toxic. Very similar to the barometer, but used to measure blood pressure rather than air pressure, you've probably seen a sphygmomanometer in the doctor's office, though many of these mercury-containing instruments have been replaced by digital versions. Look carefully to see the column of mercury and the dire warning label. Pendulum clocks measure time by counting swings. The time it takes a pendulum to swing depends only on its length. On hotter days, the pendulum expands and becomes longer, increasing the time to swing back and forth. One way to compensate is to put vials of mercury on the pendulum. When the weather gets warmer, the mercury expands upwards into the tubes, raising the center of mass of the pendulum, effectively making the pendulum shorter, causing it to swing faster, thus making up for the increased length due to temperature. Pretty clever. Some of the first computers needed a way to store data. There were no RAM chips back then. Indeed, this was before the invention of the transistor, let alone the integrated circuit. One way to briefly store data was to make sound waves in tubes of mercury. You put an acoustic transducer at one end to make the sound waves and an acoustic sensor at the other end of the tube to sense the sound waves. The sound waves are your bits of information, stored briefly in the mercury tube. To keep the bits around for more than the time they took to travel down the tube, the signal was fed back from the sensor to the transducer. The large assembly at the top of this slide is what I believe to be 18 of these tubes, making up an 18-bit memory. It's about 5 feet long, and each tube could store 384 bits. Up to 128 of these tubes were used in one computer to provide more storage. As a planetarium person, this one's a favorite of mine. This is the Spitz A4 planetarium projector, and yes, Mercury, not the planet, is involved. How do you keep projectors from shining light below the horizon when it can be in any position? A mercury eyelid, of course. Right here on the star projector are small projectors to show the celestial equator and ecliptic, lines in the sky. Here's a close-up of those projectors. See the mercury? To keep the light on the dome and out of the audience's eyes, a mercury eyelid is placed over each small projector. These eyelids are much like a smaller glass cup inside of a larger glass cup, sealed around the lip and half filled with mercury. As the cup rotates downward, more and more of the window is blocked. Since Mercury is responding to gravity, the mercury is always level with the horizon. An ingenious device. Most people have mercury in their mouths in the form of dental fillings. Not all fillings contain mercury. Some are made from a mixture of glass particles and plastic, or even gold alloys. But the most common are made from a mixture of about half mercury and the other half an alloy of silver, tin, and copper. When mercury is mixed with these solid metals, it forms a soft, squishy metal called an amalgam that can be pressed into the cleaned cavity, where it then hardens into a very tough, solid filling. Even though these are half mercury, they're considered by the American Dental Association and the FDA as safe for most people. An important feature of the amalgam is that it expands and contracts with temperature the same amount as the surrounding tooth. If the amalgam expanded more with temperature than the tooth, it might crack when drinking a hot beverage, or loosen and fall out when drinking a cool one. Much of the mercury we have in our bodies gets there from our diet. Some fish, particularly those higher on the food chain, contain higher levels of mercury. A few with higher levels are shark, swordfish, orange roughy, and ling. Lower levels are found in shellfish, salmon, and canned tuna. The mercury is usually in the form of the chemical methylmercury, CH3HG. Your body contains no mercury, or should not contain any mercury, but of course we do absorb some from the environment, as we just discussed. In any case, mercury serves no essential biological purpose. Methylmercury poisoning can cause feeling numb or dull pain in certain parts of your body, tremors, an unsteady walk, double vision, blurry vision, blindness, memory loss, or even seizures. Mercury was even thought to drive people crazy. Methylmercury can cause brain damage to developing fetuses, so pregnant women might consider avoiding some fish. Remember that red mineral cinnabar? Grind it up and you can make vermilion pigment, which has been used for several thousand years. Even though it contains toxic mercury compounds, it's still available for the careful artist. And speaking of mercury in art, I must mention this sculpture created by Alexander Calder in 1937. It uses a large amount of liquid mercury as its fluid medium. It is, of course, housed in a sealed glass room to avoid exposing the museum goers to mercury fumes. If you want to visit it, it's located in the Joan Miró Foundation in Barcelona, Spain. The Exploratorium in San Francisco also had a mercury-containing art piece by Louis Alquist, which, very similar to the liquid mirror telescope, spun a container of mercury, creating shiny mirrors. Well, until you stopped the motor spinning and the container of mercury went into chaotic motion. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about mercury. Madness, the price paid for your molten alchemy. Metal, planet, God. In the next program in this series, I'll examine an even more poisonous element, thallium. I hope you'll join me. I'm your host, Ron Hipshman. Thank you for watching this Tales from the Periodic Table program about the element mercury.